Greetings everyone, we're back here starting with section 5.1 with exponents and scientific notation. This is the beginning of chapter 5 where we're going to go from exponents to basic polynomials. So we start with exponents here, and in fact we start with the basic properties of exponents. And then we're going to see those basic properties play out with scientific notation. In this section, we will do conversion to and from scientific notation. So here are our basic properties of exponents. They all come from this definition of exponents, essentially up at the top. A positive integer exponent is simply an abbreviation for repeated multiplication. The exponent tells the number of factors. So that's what that's telling us. It's important to remember that an exponent, it's placed next to the symbol, it's juxtaposed. However, it's placed up. Therefore, the exponent itself is not a multiplication. So this definition gives us our first property of exponents. If we multiply quantities which have the same base, then we can add the exponents. And that's because the first expression, x to the m power, means m copies of x. You're multiplying that times x to the n. So this multiply is right here. That's n factors of x. So all told, you have m plus n factors of x. So the exponent keeps track of how many factors you have. We have to clarify briefly what we would mean by x to the 0. Provided x doesn't equal 0, x to the 0 equals 1, and you can verify that on your calculator. Say 42 to the, I'm using the exponent button on the calculator here, that's the little caret shape, to the 0 power, we'll get 1. Because if you have no x present, 0 x's, you still have a factor of 1. Okay. Just for completeness, if you try to do 0 to the 0, you'll get an error because domain error means that the thing is not defined for that input value of x. Now, if you're dividing with the same base, then you subtract the exponents. What that means is if you have x times x times x, and you have x times x times x times x, some of these, since they're all being multiplied, some of these will divide off. X divided by x makes a 1, 1, 1. And when you're done, you'll have some of the factors of x either show up in the bottom or the top. And that's, you essentially removed factors of x by dividing. Then finally, a negative exponent means reciprocal. Reciprocal means 1 over whatever it is. And in this case, it's the x to the positive n that you're doing 1 over. So here's some practice problems. I'm going to show you on the calculator, even though it says don't rely on a calculator to do this. This is something that you should be able to do on a test without a calculator. We're using properties of exponent here. Now notice we have the same base. That allows us to use the additive property of exponents. So we're multiplying the same base. The base will stay the same. And then we'll get the sum of the two exponents. So we will get 2012 to the 1, 3, 5, 9, which is an incredibly huge number. And in fact, if you were to try to do this on a calculator, you would get an overflow error. 2, 1, 2 to the, using the exponent key, 1, 3, 5, 9. Overflow error means that the number is too large to represent in the memory of this processors. So clear that off, clear that off. Negative 5 to the 0. Now watch here, we're doing a negative of something. That's the same thing as negative 1 times. I'll write this here once for emphasis. That's negative 1 times 5 to the 0. Negative 1 times, that's multiplication. Multiplication goes after exponents are done in the order of operations. So here we're going to be doing a negative 1 times. So it's going to be really a negative times 5 to the 0. And we know that 5 to the 0 is going to be 1. So this is going to be negative times 1 or negative 1. In contrast, if we had this problem, negative 5 all to the 0, well, any number except 0 to the 0 power is 1. Now I'm going to confirm that with the calculator. If I say negative 5 to the 0, I get a negative 1. If I put it in parentheses, negative 5 to the 0, then the exponent acts first, and you get a positive 1. In part C, we're doing a multiplication with 3 factors. Each of them has an exponent, so we can since the base is the same in each factor, we can have one base with the sum of the exponents. Now, a second ago I said that each of them has an exponent. There's no exponent over top of the x, but there is essentially a 1 there because you have one factor of x. The exponent counts the number of factors. So x to the 1 doesn't need to be written, and in fact in simplified form the 1 is not written. Remember that when it says simplify your answer, if you get down to x to the 1, you write x as the simplified answer. So here we have 1 plus 12 plus 20. The exponent is simply counting how many copies of x we have available to multiply, and we have 1 plus 12 more is 13 plus 20 more is 33. So we're multiplying all told 33 copies of x together. The exponent tells you how many copies of the base you are multiplying together. Now, here we're dividing. You can approach this division 2 ways. It's going to be a little bit crowded here, so I can simply use the quotient rule with like bases, and I can do a to the 15. Since we're dividing by a to the 20, I would subtract 20. Then we're also doing b's. We're multiplying b to the 4. Then we're dividing that by b to the 1. So remember that b right there was actually a b to the 1. And since it's on the bottom, we're subtracting it. So we have a to the negative 5, b to the 3. Now if you look back on the last page, they said that they want positive exponents only. That's usually what people consider simplified forms. So if we're simplifying, we want positive exponents only, we've got to do something with that negative 5. Well, anything with a negative exponent is really a reciprocal. Negative exponents mean do the reciprocal. So if it's on the top with a negative exponent, shove it to the bottom. If it's on the bottom with an exponent, shove it to the top. So b to the 3 can stay where it is, a to the 5 goes to the bottom. There's your simplified answer. Now I'm going to show you another way to think of this. I really don't care which way you use on an exam. I think that you need to know and understand what's going on in both of these, but there's no reason not to do it this way if you're comfortable with it. I'm recopying the problem. Now, first I'll address the A's. You have 15 copies of A on the top. You have 20 copies of A on the bottom. Well, I'll write an intermediate step here just once so that you'll see why I'm doing what I'm about to do. A to the 15. A to the 20 is really A to the 15 times A to the 5, because with like bases we can multiply the 15 times the 5 and get back to 20. Likewise, B to the 4 is really a B times a B cubed, all over top of a B. So notice that what's going to happen here is the A to the 15 divided by an A to the 15 makes a 1. We call that canceling, but really we're dividing factors. Remember, by bumping things together, everything is multiplied. So something divided by itself makes 1, and multiplying a fraction by 1 doesn't change it. Likewise, over here, a b divided by a b is 1. So these two things we call a cancellation, and we're left with a b cubed over top of an a to the 5th, which is exactly what we had over here. So that's the intermediate step if you want to go all the way through that. Normally what we do is this: a to the 15th, b to the 4th. We can do a little bit of a shortcut that's safe, provided we write the problem down correctly. So we can do this problem by saying we'll take off 15 copies of A from both of these and leave a 5 here. We'll take 1 copy of B off here and leave a 3. So what we have left is a B cubed and an A to the 5th. So B cubed over A to the 5th. And that saves us a little bit of work. Like I said, I don't care how you do it. I just want you to understand all of these. You probably ought to aim to where you can do it this last way, because it will save you a lot of effort as we move into more complicated stuff where the exponent operation itself is one small step in a larger problem. Now, on to part E. This is a common test question. What they're trying to do is make you think that you're multiplying. They got a negative and a negative, but this is not multiplication. This is exponentiation. And a negative on an exponent means 1 over. That's what that negative means. So you've got 1 over negative 5 to the 3 power. Well, now you can actually do the exponent. You're going to have negative 5 times itself 3 times. That's going to equal, first off, you've got an odd number of negatives multiplying, so you'll have a negative. So our answer will be negative. Then 5 times 5 is 25. 5 quarters makes $1.25. Now, let's see. The problem in part F has a couple of things that we have to deal with. First, there's a numerical part of the fraction that we'll actually do separately. It'll involve just regular reducing fractions. And then we have to think about the exponents. I myself like to deal with any negative exponents first. I mean, if you want to, you can just do -3 minus a -4 and get what you get. But I find that if I do a little bit of pre-processing on this, I'm happier with the result. 15 and 18 have a common factor. So I'm pre-processing the numbers first. 3 times 5 makes 15. And then I'm using this property of negative exponents. A negative on the 3 means shove it to the denominator. So that means that x cubed will show up in the denominator. A y to the 5th stays where it is. Now 18 is 3 times 6. A negative on the 4 in this exponent means it goes to the top. A negative moves to the other part of the fraction. That's what reciprocals do. Likewise, a y to the -1 goes to the top as a y to the 1. We're multiplying everything. Now, we can reduce the fraction. We can divide 3 by 3 and get a 1. So the 3's effectively go away. We have 4 copies of x on top and 3 on the bottom. So 3 copies of x take away 3 of these, and we're left with 1 copy of x on top. So we're left with 5 times x to the 1, which we write just as x, times y to the 5th, times y to the 1, and we're going to do one more step of simplification because I didn't get it all done in that one step, but that's no big deal. So we will have 5x y to the 6th over 6. That would be the same thing if somebody wanted to write it as 5/6 times x y to the 6th. So either one of these is okay. Now this one is again a problem trying to confuse us with negatives. Simply remember that a negative exponent, as soon as you see that, that means 1 over. This negative exponent means 1 over. In the first case, it was a 1 over a 4. In the second case, it's a 1 over a 5. And this subtraction comes down in between where it was. So this is really saying 1/4 minus 1/5. In order to do that subtraction, we'll need a common denominator, which with 4s and 5s, your denominator would be 20. So I'll multiply top and bottom here by 5, get 5/20ths, subtracting, then multiply top and bottom here by 4. 1 times 4 is 4. 5 times 4 is 20. So now we have the same denominator, and we have 5 minus 4 of these things. That makes 1 over 20. So that would be our answer. Now, part H, once again, you've got numbers here which are way too large to try to do with any calculator. So we have to think our way through this one. I really don't like the negative exponents. I'm going to use the reciprocal property of negatives to take care of this. I mean, I know I could subtract them, but I don't like subtracting negatives either. So 11 with a negative on it as the exponent. A negative exponent means move it to the top. So the 40,101 is going to the top. the negative 40,102, that means reciprocal, that goes from the top down to the bottom. Okay, now we've got 40,101 copies of 11 on the top. We've got 40,102 copies of 11 on the bottom. That means we have one more copy of 11 on the bottom than we do on the top. So if we cancel all these off, we'll be left with 1 down here. So we will have 11 to the 1 power on the bottom. Notice that they're all gone up here. That doesn't mean that we have 0 up here. It means that we have 11 to the 0. We have 0 copies of 11 up here, which in simplified form, we would write neither of these exponents. 11 to the 0 simplifies to 1. 11 to the 1 simplifies to 11. So we have one more 11 down on the bottom than we do on the top, 1 over 11. Here we're actually working with a pair of monomials being multiplied together, so we actually get to really use our properties of exponents here. Probably the simplest thing to do is just go through and multiply everything with a like base. First off, that means we'll multiply the numbers together. Then we'll multiply everything with a base a. So since we're multiplying, we'll get 3 plus negative 1. Then we'll multiply everything with a base b. There's no exponent on the b, that means a b to the 1. And we're multiplying another b factor, so we'll add the exponents 1 plus 7. Then we move on to c's. There's an exponent of 2 plus negative 3. Then we go about resolving what we've got there. Here we have multiplication with a negative number. So this has nothing to do with exponents with negative numbers. This is multiplication with a negative number. We get a negative 15. Then, up over top of the a, 3 plus a negative 1 is a 2. Over top of the b, 1 plus 7 is an 8. Over top of the c, 2 plus a negative 3 is a negative 1. I'm putting in the multiplication dots just for emphasis that we are multiplying all these things here. Officially, we don't need them. Juxtaposition means multiplication. Now, we have a problem here. We're not allowed to leave a negative exponent. Negative factors are okay. But negative exponents, the instructions said, don't leave those in your simplified form. So we have to fix this. The c to the negative 1, that means do c to the 1 in the denominator. Well, anything to the 1 power is itself. So we're going to have negative 15 a squared b to the 8th over top of c, which is the same as c to the 1. In simplified form, people tend to prefer to have a negative factor out in front of the fraction. You could put it on top or bottom either way, but people normally like to keep the negatives out where they're more accessible. Now we convert to scientific notation. Remember that the thousands place is a 10 cube. 10 to the 3 power is 1,000. The millions place is 10 to the 6th. The commas group things in 3 zeros. Well, that means you're going up by 10 to the 3 each time. 10 to the 3, 10 to the 4, 10 to the 5, 10 to the 6th. So this would be the billions place, or 10 to the 9. And then this 3 is in the trillions place. That's 10 to the 12. So the 5 is in the 10 to the 13 place. So we can write this as 5.3103 times 10 to the 13. Traditionally, we use the St. Andrew's cross to represent multiplication with scientific notation. There is absolutely no reason that you can't use a dot. This equals 5.3103 times 10 to the 13. You just have to make your dot clear. The dot is preferable if you've got the variable x running around. So if you have a factor of x in here, don't use the St. Andrew's cross, use the dot. Remember that in scientific notation, this number has to be bigger than or equal to 1, and it has to be less than 9. So it's got to be exactly a one-digit number on the left of the decimal point. Now, the tenths place in part B, that's 10 to the negative 1, 1/10. That's the hundredths place, so that's 10 to the negative 2. There's 10 to the negative 3, 10 to the negative 4, 10 to the negative 5. This is, the 4 is in the 10 to the negative 6 place. And all I did was count from the decimal starting at negative 1. 10 to the negative 1, negative 2, negative 3, negative 4, negative 5, negative 6. So this has got to be 4.301 times, however you write it, 10 to the negative 6. Go the other way. The 10 to the negative 8 means we're dealing with a small number, so we have to have the 5 land in the 8th place after the decimal. So there's 10 to the negative 1, negative 2, negative 3, negative 4, negative 5, negative 6, negative 7, negative 8 is where the 5 goes. Make sure I count it. Mathematicians are really bad about counting. So let's see, 1, 2, 3, 4, 5, 6, 7, 8. Then copy the rest of the number, 2, 3, 0, 1. One of the reasons we use scientific notation is because it's so easy to miscount with all these zeros. This is much less error prone to write. It's a much more compact and safe way to write an incredibly small number, or in this case, an incredibly large number. 10 to the 13, well, that's going to be trillions again. In fact, if I'm not mistaken, that's almost the number we had in part A. So you're going to have 5, 2, 3, 0, 1. This has got to be in the 13th place. So this is the 12th place. So that's a place that gets a comma. So every 3 places gets a comma. So there are 3 zeros there. There have to be 12 digits to the left of 10 to the right of 10 to the 12. Well, there were 6. There are 3 more. There are 3 more. Once again, this is an incredibly awkward number to be dealing with. It's much better to deal with this in scientific notation. And in your science class, you'll find out that this is the way we want to deal with them, because we can keep track of a thing called significant digits, or sig figs, much more easily if we write them in scientific notation.